Hello and welcome to Postgres FM, a weekly show about all things PostgreSQL. I'm Michael, founder of pgMustard, and this is my co-host Nikolay, founder of Postgres.ai. Hey Nikolay, what are we talking about today?
Your choice, and it's toast, yet another boring topic.
Yeah, I think it's the tastiest breakfast snack. So I thought you might actually want to talk about it being, food related.
Well, okay, but I agree that this is something that everyone should learn, at least in some detail. Not maybe deep, but all developers should understand how Postgres stores data and why limits are so good. We can store up to 1 gigabyte of data in a single column, in a single row, in a single column. A single cell, if you speak simple language. And it's great. So you can insert really large values usually.
Yeah, this is one of my favorite kind of types of Postgres feature in that it's on by default. It does something that most people never have to worry about.
The correct
it's exactly transparent and on by default, and it helps in so many ways that you might never have thought about, or you might only hit a limit. And I love this kind of thing because you can go through life never knowing about it, and it's still helping you out.
Unlimited toasts to everyone, almost unlimited.
Yeah, so should we start with what we're even talking about, I guess? If for anybody new to this, we're talking about how Postgres, based on a couple of Postgres limitations, specifically, you can't store a row across multiple pages, and the default page size being 8 kilobytes and kibibytes, sure, yeah. And there's one other thing that is specifically limited, I think, a 2 kilobyte limit, so that it can store at least 4 rows or tuples per page. Postgres has a way of, that if we only had that, we'd only be able to store small and medium values in Postgres, right? But we want to be able to potentially store sometimes larger or relatively large pieces of data from time to time.
Yeah, let's warm up with small topic. Maybe it's not about toast itself, but it's good intro topic. Recently, very popular YouTuber and blogger Hussein Nasser. Sorry, I always pronounce other names wrong, but they pay me for the same because my last name is very difficult to pronounce. So it was a great post, a couple of posts on Twitter, LinkedIn. How many rows can we insert? How many tuples actually? Let's speak correct language here because we are on Postgres FM podcast, right? Not rows, but tuples or tuples, as you prefer. How many of them we can insert? How many of them can fit into one single page, which is, as you said, by default 8 kibibytes? And it's a great question to understand the internal layout. There is a page header, and it's some static amount of bytes. Number of bytes is 24 bytes, and each page is allocated for page header. Then we have, from both directions, we fill page with some data. From the beginning, we fill it with pointers to tuples, pointers to entries, right? And each one is only 4 bytes. So each tuple in page, the pointer takes 4 bytes, and they start from the beginning. But real data comes from the end of the page, right? And of course, the size there depends on the data itself. But each tuple there always has a header as well. Tuple header, and it's 23 bytes, but due to alignment padding, it's padded to 24 bytes. So alignment padding, it's for performance reasons. Everything data should be fetched in so-called words of 8 bytes. That's why 24, not 23. And it means that we can fit a few hundred of tuples, right? But interesting point that you can create a table without any columns at all, right? That's interesting. So you can create table, parentheses, that's it. can create table T1, for example, parentheses. That's it, semicolon. And Postgres allows it. Of course, it's not like standard thing, but Postgres allows it. Why not? We will always have internal like virtual system column, ctid, xmin, xmax, as we discussed a few times. So you can select ctid and it will provide page number and offset there. Offset, this is like exactly this pointer. And so we can start inserting to T1 select. Again, select in Postgres, select clause allows empty list of columns as well. It's some kind of trick. And this is how you can reach a little bit more tuples inserted to page, 291 tuples. And the overhead is huge, actually, in this case. But I would like to say it's not 100% because number of columns, number of rows or tuples we have, it's also some knowledge, right? But yeah, almost 100% wasted for overhead for various headers and pointers.
Yeah, so we're looking, I guess that's the theoretical maximum number of
practical as well. I did it, but nobody wants empty.
But it's not useful, right? Yeah, if you're storing
testing,
data,
maybe in some testing, sometimes it's useful.
But it does mean that in practice, we'll only ever have a maximum of a few hundred rows per page, even if you're only storing very, very small amounts of data. But I guess we're talking about the opposite in this case. We're talking about the other end of the limit.
Yes, this is extreme. I just wanted to give wider understanding of what we talk about. This is extreme situation when we have no data at all in the table, and we can have 291 tuples. Then we start having some column, for example. An interesting thing, it doesn't matter. Like smallest column probably will be 1 byte. If you take, for example, Boolean, Boolean is 1 byte. Already a lot of waste, right? Because it's not bit, it's byte. But we this is how the world we live in. Like we need, there's a lot of overhead in the relational approach. Of course, if you need to store some bits, probably you need to create some additional storage or pack them to bytes and store somehow differently. But take, for example, 1 byte data type. Again, it will be padded till 8 bytes, and you will be able to store only 226 rows because of this overhead immediately. The same for regular integer, which is 4 byte. It will be padded with 4 zeros in each value, or integer 8 or big int data type. They all will take the same storage, and you will be able to fit only 226 tuples into a single page, right?
Yeah,
quite straightforward. and if it's timestamp with time zone, which it both takes 16 bytes, okay, you will have less. You will be able to fit fewer tuples or rows into a page. Tuples more correct, because they might be just 1 row but many versions of it, right? So now let's go to Toast now, finally, right? We add more and more, or for example, we decide to have a column of from Varlina family of data types. Varlina means variable length. For example, text, varchar, JSON, XML.
Previous episode. Yeah.
Or numeric, for example, as well. Because numeric is exact number and it can take a lot of data. So it's also Varlina.
Interesting. But yeah, typically this would be a text field or a JSON field. That's pretty common, isn't it?
Right. And so they all behave similarly, and they all involve this mechanism Toast, which works implicitly, transparently. We usually don't think about it until we deal with some performance issues and we need to understand what's happening under the hood. But so what is Toast? Let's let's discuss it.
I was really interested in where the name came from, and I looked into the mailing list, and I think the original reason for calling it Toast, so it's an acronym, but the original reason was it's about slicing. So if we go back to the page size, and let's say we're just trying to insert an 80 kilobyte blob of text. Now, to fit that, we can't fit that in an 8 kilobyte. So I probably picked a bad format there for, let's say, a megabyte of text into an 8 kilobyte page. Naturally, we're going to struggle, and we've got the limitation that we can't store it over multiple pages. So this is a strategy for slicing that data up into multiple tuples like in a separate table, and storing pointers to each one so that we can reconstruct it, so Postgres can reconstruct it later when we request it. So this is it also, by the way, includes compression. So that I'm sure we'll come to that. But by default, we'll first try and compress it, and if not, we'll store it off page. And so the name comes initially from slicing, and I think there's some funny, like, people kind of working backwards into acronyms, which I think is how a lot of things end up getting named. But it's something along the lines of in fact, I can read it off my notes. I think the generally accepted one is the Oversized-Attribute Storage Technique, and it had a code name of Toast, or the best thing since sliced bread, which I found funny. And I'll include the mailing list thread there for anybody interested in that.
Yeah, imagine toast with gin, how they work together, right?
Yeah.
So about technical aspects of it, very roughly, when our total length of all columns involved and one tuple value approaches roughly 2,000 bytes, this mechanism starts working. There are many details inside it. We like, podcast probably not the best place to discuss everything, because like there are many if, else, and so on details how it works. But roughly, Postgres tries to fit at least 4 values in one page. That's why actually I wanted to bring this topic of the maximum number. But at least let's have at least 4 values in one page. It means we need to shrink value to chunks of roughly 2,000 bytes, and some data will be in the main page, but other chunks will go to a separate table, which automatically created, called toast table. For each regular table, we can have up to only one toast table, right? But it can have many chunks for each value, and this is interesting. What should we discuss about it? Let's talk.
Yeah, I think so. There's a couple of things. One, kind of like the performance implications of that, both good and bad. Also, I guess, when do we need to worry about? We've got certain values certain things that can be changed. Should we ever change those? There's default compression, for example. There's default whether this is even on or off. There's a few things to be wary of, like the usual kind of select star, or even whether we should store. We can use Postgres' version of this, or we could avoid storing this data in the database at all. That's a common technique. We could store it ourselves deliberately in a separate table to avoid some of those issues. Like, I guess we could discuss some of those pros and cons. Which direction would you like to go?
Yeah, well, first of all, it's, as we already discussed on previous episode about JSON, nothing can beat narrow cases when we have really small number of columns. All columns are small. Like, even if Varlina data types involved like text, the actual values are small. Everything fits like roughly. All total values of tuple is less than 2,000 bytes. By the way, the easiest way to check the size, it's really interesting. You can select T1 from T1, taking row record. You you can convert it to text, and you can convert it. You can get length of it. But also there are special functions, PG column size. I don't remember by name on top of my head, but it's possible also to check it more like wisely. But I quite often I use this trick to converting whole record to text and just checking the length of it. So if everything below 2000, nothing can beat this, because toast is not involved, so there is no overhead. Because of course, if you need to read whole tuple, you need to join with, like, Postgres needs to join with toast table and multiple records, get and extract multiple records from toast table, and then collect everything, and it takes time, of course, and there is overhead here. Without toast, it's much faster. Obviously, that's why we discussed in JSON episode, if JSON values are below 2000, performance is much better. Once we approach roughly 2000, we have some degradation because toast starts to be involved. But interesting thing that there are many things we are done to make toast quite efficient in terms of performance. For example, we know MVCC Postgres model, when you update some row, a new tuple is created, and the old tuple is stored also until AutoVacuum deletes it, seeing that it's not needed anymore. Not all transactions can look at it. So for toast, it's slightly different. Right. So in toast, there is like special versioning applied, and it's quite reduced. So only inserts and deletes and updates trigger inserts of toast values only if toast value actually changed. If you change some different column, the same toast records, toast is regular table actually, right? From first glance. But update happens in the main page. It can be hot update actually inside this same page, very efficient, not involving index, not causing index amplification problem. But toast, we just reuse the same records for new actual tuple in main page, right? In main table. And this is quite interesting, and this adds efficiency as well, right?
Yeah, very much so. And I read another cool thing, which is that the large values from the toast table are only pulled out if they're selected at all, and they're only pulled out at the time the result set is sent to the client. Now that's super interesting for things like in memory processes. So if we're, like, for example, if we're sorting rows, and we're carrying like large rows around, that's going to take up a bit more space in memory. And if we only have to pull out some of that larger information at the end, chances are more of that's going to be done, quicker and with less footprint. So it's super interesting, some of the benefits this comes with, but some of the other things we mentioned don't.
This really means cool. Putting all columns into select clause, which sometimes ORM can do. It can cause issue with performance. You can be much more efficient if you select only those columns you really need at this moment, right?
Yeah. So I think
Projection.
It's slightly different. Yeah. So this is a typical select star from problem, isn't it? Now that has other issues, like what happens if you add a column? Select star is kind of can change on you.
It's convenient, right? You have everything.
For anybody who's listening on audio, Nikolay has got a smirk on his face, and he's definitely joking.
Right. So what about compression? There is automatic compression applied, which is lightweight, not like super high ratio, producing not super high ratio, but it doesn't consume too many CPU cycles.
Yeah, I guess for anybody trying to test this out, in fact, I read a good blog post of somebody trying to test out Toast, and it looks like the first example they picked actually didn't trigger a Toast table as they were or didn't trigger any chunks to be inserted into a Toast table, because the value they were inserting, whilst it would be 2 kilobytes of text, it compressed really well because they were just doing a repeat character, for example.
So you're saying it was compressed before going to Toast tables, and it could fit main table. Main table
exactly.
wasn't enough.
In fact, that's a better way of describing it. At first, if the whole tuple, as you mentioned, looks like it's going to exceed 2 kilobytes, the first thing that Postgres tries to do is compress like one, or it presses as many of these toastable values as it can to store them on the page still. And only if it can't will it then move them off the page into the Toast table. So that's a really important thing. That's on by default. That can be like every combination of this is possible. But yeah, by default, it will try and compress, and it will by default use, and this is something I didn't realize until a year or two ago, it will use a Postgres, a pgLZ compression algorithm. And since Postgres 14, you can use LZ4, is it?
You can control. I don't remember, but there are options in new Postgres. There are options to control it. But I would like to emphasize that you also can control and tell Postgres not to try to compress, because if you, for example, have some value which you know already compressed, it would be not good in terms of efficiency to try to compress it once again. So you can tell Postgres to have like something like storage external. In this case, it would go to Toast immediately without compression attempts at all.
Yeah, exactly. So really good point. You do pay an overhead. Like I think one of the benefits of LZ4, I think it's well, with compression, there's normally like a trade-off, right? It's how well it compresses, like versus speed of compression versus speed of read. And the benchmarks I've seen, LZ4 does come out on top, but I guess it will depend on the exact scenario. But as you say, if it's already compressed, it doesn't matter what algorithm you're going to use. There's going to be overhead for no real benefit.
Right.
So
I'm not a big compression expert, but of course there are many like recent advances in this area, not only PyPiper and so on. And it was like, for example, Brotli. We use Brotli quite often for Vol-G compression of vols when we do backups. But I'd like to say that it's good that we have more controls. It's very good. But recently we had a brief, small, like word battle with CTO of Victoria Metrics, and they mentioned that we discussed number of rows versus terabytes of data. For example, 1 terabyte for me is always something like 1 billion of rows, roughly, and for them it's roughly 1 billion of rows is 1 gigabyte of data.
Wow.
So it's like 3 orders of magnitude difference. Yeah. Why? Because they talk about time series often, for example, Victoria Metrics, right? ClickHouse, column store, and they live in very different world. Unfortunately, with Postgres, we still don't have quite good battle-proven column store. There are attempts. There is ongoing work. Several teams working on it, we know. But when we talk about compression, it really shines when we have column store.
Yeah, because the data is more similar, right? Like,
right. Because when you try to compress values in raw, not involving the context of other values in the same column, you are in worse position. So the compression topic. Actually, Peter Zaitsev interview happened this week on Monday on Postgres TV. A very good chat it was. This is his idea that you should consider compression and expect good results only if you combine this topic with storage engine topic. And for column store, it's much better. Or like Timescale, they are very smart. They still work in row store, but they apply compression looking at column. It's a really interesting article. We already discussed it a few times, so worth referencing it once more time. But again, in some cases, some compression in place, it's good, and it's good that we have more controls in Postgres 15.
Yeah,
but I hope in future 14, sorry. I hope in future Postgres versions we will have in core product we will have column storage engine providing the same level of compression, like maybe not 1000x but 100x, and in this case we will also say, okay, 1 billion rows, it's not 1 terabyte anymore, it's like 10 gigabytes maybe. Right?
Yeah. Should we talk about some of the limits of Toast? Like, what's the maximum size of
1
row?
gigabyte for one value? I don't remember. The limits are quite good, but sometimes we hit them. And for me, the biggest limitation is that Toast is not applied. Like for indexes, it's not applied. There is compression there. I don't remember details, but I remember like you cannot index really huge value of like 100 megabytes. You cannot index it. You need first maybe hash it and index only some expression. So this is one of the biggest limitations because in toasting, it's applied only to heap, right? This full-fledged toasting. So this is one limitation. 1 gigabyte for values, another limitation. What else?
I've read a couple more in the docs, but I don't think you're likely to hit them. So, for example, you can't have more than 4 billion toasted values in a single table, which would be a lot given they all have to be over a certain size. You know, we're talking about terabytes of data.
Well, I can easily imagine that we can hit it, but before that, we probably will face other performance issues. So everyone with table more than 100 gigabytes should already use partitioning.
This is another benefit
facing
of partitioning.
Other performance issues, but it's another story.
And then one more kind of slightly hypothetical one. Please don't do this, but you could, I think in theory, you could only have about 450 wide columns in a table.
How many?
450 columns that are toastable or something. Yeah. It's a lot.
It's a lot, but still I already saw cases when it was achieved.
Yeah. So yeah, pretty big numbers, but things to be aware of if you're working in an extreme case for some reason.
Right. And if you care about if storage efficiency, my advice is to learn about column Tetris in Postgres. This is quite common term already, and I usually there are two approaches: either start from big and go to small, or vice versa. I prefer starting from small columns first. For example, all 1 byte, 2 byte columns go first, then we have 4 byte columns, 8 byte columns, 16, and then all Varlina columns go last. In this case, you probably will have fewer zeros due to alignment paging and spend fewer bytes, maybe sometimes gigabytes actually, or hundreds of gigabytes if you have really big data volumes for storage. And it's not only for storage, it's also for the size, the amount of RAM, both for shared buffers and page cache, and also for backups, and so on and so on. Sometimes the benefits of applying better column Tetris tactics are good. And toast, toasted like Varlina toast should go last, and in this case, it's good. If you mix them, this is worst case. For regular integer, some text. Regular integer, some text. In this case, you will have a lot of zeros due to alignment paging.
I read a good post by Braintree, who I think built something to help kind of, it's almost like repacking a table. Like, for example, you can sort out a column ordering that makes sense initially, but then what happens if you add a couple of columns? Does the order still make sense? For large enough tables, they found it could be worth changing it. So
Well,
that's a really good.
I also build it. I have a small report. Actually, it's not small. It's recursive CTE with recursive analyzing this for any table and proposing better order. It's in my Postgres DBA, quite old tool, like ad hoc tool to analyze some Postgres cluster aspects. So
Nice.
Yeah, and some people use it, I think.
There's one more blog post I wanted to mention before. It's kind of on this topic, but kind of not. Is by Haki Benito. I've mentioned it in a couple of episodes, but this is almost a side effect of the fact we have Toast. Is he noticed that there was some kind of medium-sized text? So he defined small text as being, like integers, timestamps, small numbers of bytes per column, and then large text being kind of like the blobs we're talking about here. Whole HTML pages or larger things that automatically going to be quite big and off, and therefore off the page. He mentioned there was he called it surprising impact of medium-sized text. So kind of still text fields, or it might be a comment on a blog or something, could get quite long, could get into the multiple kilobytes even, but or just about still fits on the page. So it's below that threshold we were talking about, 2 kilobytes compressed. Now these, if you start to only have, for example, that limit of 4 tuples per page, and you they're getting towards 2 kilobytes each, suddenly if you're doing reads of multiple pages, if you're doing kind of scans, you could be having to read quite a lot of data for the amount you're returning. If you're not returning those columns, if you're not returning, for example, the comments, you don't need them for the query you're doing. You're still having to go through quite a lot of pages. So efficiency wise, those sometimes you might want to deliberately store yourself in a different table so that you can fit much more data on the pages that you are scanning more frequent.
Yeah.
So it's a really interesting blog post.
Sometimes one-to-one relationship might seem strange, but it makes sense. So one table is for very compact storage and another for bigger values.
Yeah, exactly.
But in this case, you always should remember that there are no indexes on top of 2 tables. So you lose some index-only scan, for example, or index scan opportunities, right?
Absolutely. Was there anything else you wanted to cover on this one?
No, just that's it, I think, right?
I think so. Thank you everyone for joining us. Thank you, Nikolay. See you next week.
Thank you. Thank you. Bye-bye.